So do the math. How many stars are there in the visible universe? 100 billion galaxies times 100 billion stars per galaxy. We're talking about a number beyond human imagination.
Have you ever looked up at the night sky and wondered about the mysteries of the universe? Have you ever asked yourself questions like, how did the universe begin? Or what is the nature of dark matter and dark energy? If so, you're not alone. For centuries, scientists and philosophers have been trying to unravel the secrets of the cosmos. In today's video, we'll be exploring the topic of the theory of everything and the quest to understand the universe. Our current understanding of the universe is based on centuries of scientific discovery and observation. Thanks to advancements in technology and the work of brilliant scientists throughout history, we have a good grasp of the laws of physics that govern the behavior of the universe. However, despite our progress, there is still much we don't know. One of the biggest challenges facing scientists today is the quest for a theory of everything. This is a single, unified theory that explains all the fundamental forces in the universe, from the tiniest subatomic particles to the largest cosmic structures. Although we've made significant progress towards this goal, we still have a long way to go. Another challenge we face is the fact that much of the universe is invisible to us. Dark matter and dark energy, which together make up about 95% of the universe, are still shrouded in mystery. We know they exist, but we don't yet understand their properties or how they interact with normal matter. So, why is it so important that we continue to pursue the quest for a theory of everything and strive to understand the universe? Well, for one thing, it helps us to better understand our place in the cosmos. It also has practical applications, such as helping us to develop new technologies and solve problems related to space exploration. Stick to end of this video, as we'll be exploring the history of science and the universe, the Big Bang Theory and cosmic inflation, the standard model of particle physics, the unification of forces, dark matter and dark energy, and the multiverse and the future of the universe. So, buckle up and get ready to explore the mysteries of the universe. To understand our current understanding of the universe, it's important to first look back at the historical context of the scientific discoveries that led us here. One of the earliest figures in the study of the universe was Aristotle, a Greek philosopher who believed in a geocentric model of the universe, where the Earth was at the center and everything else revolved around it. While his model was ultimately proven incorrect, his observations and ideas about the universe were groundbreaking for his time, where figures like Galileo and Johannes Kepler made significant strides in understanding the laws of motion and the nature of planetary motion. Galileo was famous for his use of the telescope to observe celestial bodies, while Kepler discovered that planets move in elliptical orbits around the sun. The 18th century saw the birth of modern physics with the work of Isaac Newton, who developed the laws of motion and gravity. He also showed that the same laws applied to both the motion of objects on Earth and in the heavens, paving the way for a unified understanding of the universe. Fast forward to the 20th century, where Albert Einstein revolutionized our understanding of space and time with his theory of relativity. His famous equation E=mc² showed that energy and mass were interchangeable and led to the development of nuclear power. Another key figure in modern physics was Stephen Hawking, who made significant contributions to the study of black holes and the origins of the universe. His work showed that black holes could emit radiation, which became known as Hawking radiation. Each of these figures built on the work of those who came before them, leading to our current understanding of the universe. Aristotle's observations laid the foundation for future scientific inquiry. Galileo and Kepler expanded our understanding of the laws of motion and planetary motion. Newton developed the laws of gravity and motion. Einstein revolutionized our understanding of space and time. And Hawking made significant contributions to our understanding of black holes and the origins of the universe. The historical context of the scientific discoveries that led to our current understanding of the universe is a fascinating journey that showcases the incredible progress we've made as a species. From ancient Greek philosophy to modern-day physics, each contribution has built on the work of those who came before and pushed the boundaries of our understanding. The origins of the universe have been a topic of debate and fascination for centuries. However, the Big Bang Theory has emerged as the most widely accepted theory explaining how the universe began. According to this theory, the universe began as a singularity, a point of infinite density and temperature, and has been expanding ever since. But how do we know that the Big Bang Theory is true? One piece of evidence is cosmic microwave background radiation, which is the afterglow of the Big Bang. This radiation can be detected throughout the universe and shows that the universe was once much hotter and denser than it is now. However, the Big Bang Theory doesn't explain everything. For example, it doesn't explain why the universe is so uniform on a large scale. That's where cosmic inflation comes in. Cosmic inflation is a theory that suggests the universe underwent an incredibly rapid expansion in the first fraction of a second after the Big Bang. This would have smoothed out the universe and could explain why it's so uniform. So, how does cosmic inflation work? The basic idea is that a small patch of the universe expanded incredibly rapidly, causing it to stretch out and become much larger than it was before. This process would have happened many times, with each patch of the universe expanding and smoothing out the universe even further. But is there any evidence to support the theory of cosmic inflation? Yes, there is. Another piece of evidence comes from the large-scale structure of the universe. Observations show that the universe has a clumpy structure, with galaxies and clusters of galaxies forming in long filaments and sheets. This structure is also consistent with the predictions of cosmic inflation. The Big Bang Theory and cosmic inflation have revolutionized our understanding of the universe. The evidence for these theories is compelling, and they have helped to explain many of the mysteries of the cosmos. However, there is still much we don't know, and scientists are continuing to explore the origins of the universe and the nature of cosmic inflation. The Standard Model of particle physics is one of the most important and successful theories in modern physics. It is a theoretical framework that explains how subatomic particles interact with each other through the fundamental forces of nature. The Standard Model describes the behavior of three of the four fundamental forces of nature: the electromagnetic force, the weak force, and the strong force. It does not include gravity, which is still not fully understood in the context of particle physics. One of the key concepts of the Standard Model is the idea of particle families. There are three families of particles: quarks, leptons, and bosons. Quarks are the building blocks of protons and neutrons, which make up the nucleus of atoms. Leptons include electrons, which orbit the nucleus, as well as other particles, like neutrinos. Bosons are particles that mediate the fundamental forces, including the photon for the electromagnetic force, the W, A, and Z bosons for the weak force, and the gluon for the strong force. Each particle in the Standard Model has a set of properties, such as mass, charge, and spin. These properties determine how the particles interact with each other through the fundamental forces. For example, the electromagnetic force is mediated by the exchange of photons, which have no mass and no charge. The strong force is mediated by the exchange of gluons, which have both mass and charge. One of the most important predictions of the Standard Model was the existence of the Higgs boson. This particle is responsible for giving other particles mass. Without the Higgs boson, particles would not have any mass and would move at the speed of light, making the universe a very different place. The search for the Higgs boson was a major focus of particle physics research for many years. Scientists at the Large Hadron Collider in Switzerland conducted experiments to try to observe the Higgs boson. In 2012, they announced that they had discovered a particle with properties consistent with those of the Higgs boson. The discovery of the Higgs boson was a major breakthrough for the Standard Model. It provided experimental evidence for the theory and confirmed many of its predictions. However, the Standard Model is not a complete theory of everything. It does not explain the behavior of dark matter, for example, and it does not include gravity. The Standard Model of particle physics is a powerful theory that has helped us to understand the behavior of subatomic particles and the fundamental forces of nature. It describes the properties and interactions of particles and has made many successful predictions. The discovery of the Higgs boson was a major milestone in particle physics research and confirmed many of the predictions of the Standard Model. However, there is still much we don't know about the universe, and scientists continue to explore new theories and conduct experiments to try to unravel its mysteries. As we've seen in our exploration of the universe, one of the greatest challenges facing scientists today is the quest for a theory of everything. In our last segment, we discussed the Standard Model of particle physics, which explains the behavior of particles and the electromagnetic and weak forces. However, the ultimate goal is to unify all the forces in the universe, including gravity. The unification of the electromagnetic and weak forces is an important step towards this goal. In the 1960s, physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg proposed a theory that explained the behavior of these two forces as two aspects of a single force known as the electroweak force. This theory predicted the existence of the W and Z bosons, which were later discovered in experiments at CERN in the 1980s. But how does symmetry play a role in unifying forces? Symmetry is a fundamental concept in physics and refers to the idea that physical laws should be the same regardless of the orientation or position of an object in space. In the case of the electroweak force, physicists proposed a new kind of symmetry known as electroweak symmetry. This symmetry explains why the W and Z bosons have mass, which is a crucial feature of the electroweak force. Despite the success of the electroweak theory, there is still much work to be done in unifying all the forces in the universe. One of the biggest challenges facing physicists today is the unification of the electroweak force with the strong force, which holds the atomic nucleus together. This is known as the Grand Unification Theory, GUT. The search for a GUT has led to the development of various theories, including string theory, which proposes that all particles are actually tiny strings of energy vibrating in 11 dimensions. Another theory is loop quantum gravity, which proposes that space and time are not continuous, but are made up of tiny, indivisible units. But the ultimate goal is the unification of all the forces, including gravity. Gravity is the weakest of the four fundamental forces, but it is also the most mysterious. So far, attempts to unify gravity with the other forces have been unsuccessful, but physicists remain optimistic. One proposed theory is known as supersymmetry, which proposes the existence of a new set of particles known as supersymmetric particles. These particles would help to unify the forces by explaining the behavior of dark matter, one of the biggest mysteries of the universe. The unification of forces is a crucial step towards our understanding of the universe. Through the study of symmetry and the development of new theories, we are making progress towards a theory of everything. While we may not yet have all the answers, the pursuit of knowledge and the quest to understand the universe is a noble one, and one that will continue to inspire scientists and thinkers for generations to come. Dark matter and dark energy are two of the biggest mysteries in the universe. While we can't see them directly, we know they exist because of their gravitational effects on visible matter. The evidence for the existence of dark matter comes from observations of galaxies and galaxy clusters. We've observed that the visible matter in these systems doesn't have enough mass to account for the observed gravitational effects. This means that there must be additional, unseen matter that's exerting a gravitational pull on visible matter. This additional matter is what we call dark matter. Dark matter interacts very weakly with normal matter, which is why we can't see it directly. We know that it doesn't emit, absorb, or reflect light, and it doesn't interact with other forms of electromagnetic radiation, like X-rays or radio waves. This makes it incredibly difficult to detect and study. Dark energy, on the other hand, is even more mysterious. It's a hypothetical form of energy that's thought to be responsible for the observed accelerating expansion of the universe. The evidence for dark energy comes from observations of distant supernovae, which revealed that the expansion of the universe is accelerating rather than slowing down as we would expect. While we know that dark matter and dark energy exist, we still don't understand what they are or how they interact with normal matter. Scientists have proposed a number of theories to explain the nature of dark matter, including the possibility that it's made up of particles that we haven't yet detected. One theory is that dark matter is made up of weakly interacting massive particles. These particles would interact very weakly with normal matter, which is why they haven't been detected yet. However, scientists are currently working on experiments to try and detect these particles directly. Another theory is that dark matter is made up of axions, which are hypothetical particles that are incredibly light and interact very weakly with normal matter. Some scientists believe that these particles could be produced in the core of stars and then detected using specialized equipment. The nature of dark energy is even more elusive. Some scientists believe that it could be a property of space itself, while others think that it could be a new type of particle that we haven't yet discovered. The implications of dark matter and dark energy for our understanding of the universe are significant. For one thing, they show us that there is much we don't know about the universe. They also challenge our understanding of the laws of physics and the behavior of matter and energy. Understanding dark matter and dark energy is critical to our understanding of the universe as a whole. It could help us to develop new theories that unify all the fundamental forces of the universe, and it could also shed light on the ultimate fate of the universe. Let's talk about one of the most mind-bending concepts in modern physics, the multiverse. The idea of a multiverse suggests that our universe is just one of many, potentially infinite, universes that exist alongside it. It's a theory that's gained a lot of attention in recent years, thanks in part to its appearance in popular science fiction. There are many different types of multiverse theories, but one of the most well-known is the idea of a bubble universe. Multiverse. In this theory, our universe is just one of many bubbles that exist in a larger space-time. Each bubble contains its own universe with its own unique properties, laws of physics, and even different versions of ourselves. Another type of multiverse theory is the many worlds interpretation of quantum mechanics. This theory suggests that every time a quantum measurement is made, the universe splits into multiple versions of itself. In this way, every possible outcome of a quantum event is realized in a different universe. But what does the idea of a multiverse mean for the future of our universe? Well, one possibility is that our universe is headed towards a big freeze. This is a scenario in which the universe continues to expand forever, eventually cooling to a state of absolute zero. If this happens, all matter in the universe will become motionless, and life will no longer be possible. Another possibility is the Big Crunch scenario. This is the idea that the universe will eventually stop expanding and begin to contract, eventually collapsing in on itself in a catastrophic event that would destroy everything in the universe. And then there's the Big Rip scenario, which is the most terrifying of all. In this scenario, the expansion of the universe accelerates to such an extent that it rips apart everything in the universe, from galaxies to stars to planets to atoms. So, What does all of this mean for the fate of the universe and the future of humanity? Well, it's hard to say. If the Big Freeze scenario plays out, it's possible that life could continue to exist in some form, as long as it can adapt to the extremely cold conditions. But in the case of the Big Crunch or Big Rip scenarios, life as we know it would be completely wiped out. Of course, there's always the possibility that there are other universes out there that we haven't even discovered yet, and that life could continue on in one of these other universes. But that's all speculation at this point. Ultimately, the idea of a multiverse and the potential scenarios for the future of the universe are both fascinating and terrifying. They force us to confront our own mortality and the fragility of our existence. But they also remind us of the incredible vastness and complexity of the universe and the endless mysteries that await us as we continue to explore it. As we conclude this video, it's important to reflect on what we've learned. From the history of science and the universe to the current state of our understanding of the universe, we've explored some of the biggest questions and mysteries that exist. We've talked about the Big Bang Theory, cosmic inflation, the standard model of particle physics, the unification of forces, dark matter and dark energy, and the multiverse and the future of the universe. Despite our progress, we must acknowledge that there is still much we don't know. We must continue to explore and push the boundaries of our knowledge. The quest for a theory of everything is ongoing, and we must encourage future generations to pursue this quest. It's through the exploration of the universe and its mysteries that we gain a better understanding of ourselves and our place in the cosmos. So, as we wrap up this video, we encourage you to continue to explore the mysteries of the universe and to never stop asking questions. Who knows? Perhaps you'll be the one to discover the next breakthrough that will revolutionize our understanding of the universe.